Welcome to The Explainer. Today, we're pulling back the curtain on a piece of tech we all use constantly, but maybe don't think about too much. Yep, we're talking about Wi-Fi. It really does feel like magic, doesn't it? But surprise, it's not. It all comes down to some really cool physics, a clear set of rules, and of course, some seriously clever hardware. Okay, you ready? Let's dive right in.
So everything, and I mean everything, starts with the most fundamental building block of it all, the radio wave.
Okay, so imagine dropping a pebble into a pond. You see those ripples, right? Well, frequency is just how fast those ripples are moving up and down. A signal that vibrates slowly has a low frequency, and one that vibrates really fast, that's a high frequency.
So when we talk about measuring this, we use the term Hertz. If a wave does 4 of those up and down cycles in 1 second, its frequency is simply 4 Hertz. Easy enough, right? And this simple measurement is absolutely key to understanding why our Wi-Fi performs the way it does.
So this is actually a choice you make all the time, maybe without even realizing it. Think of the 2.4 gigahertz band like a long, winding country road. Yeah, it can go a really long way, and it's great at getting through obstacles like walls, but it's also slower and can get super crowded. Now the 5 gigahertz band, that's your multi-lane superhighway. It's way, way faster, but the trade-off is it doesn't have the same range and it gets blocked by walls much more easily.
And I love this party analogy because it's just perfect for understanding channels. You see, those big frequency bands are split up into smaller lanes or rooms. If way too many devices are all trying to use the same channel, it's just like a packed room where you can't hear a thing. So picking a less crowded channel means a much better, clearer connection for you.
Okay, so having different speeds and lanes is a great start, but for all of our devices to talk to each other without total chaos, they all have to be speaking the same language.
And that shared language, that rulebook for Wi-Fi, is set by the Institute of Electrical and Electronics Engineers, or IEEE. This standard is the whole reason your phone, made by one company, can talk to a router made by a totally different one, anywhere on Earth. And just look at how much that language has evolved. We started with early standards like 802.11a and G, topping out at about 54 megabits per second. Then, 802.11n was a huge leap forward, using both bands to get us speeds up to 600 Mbps. Now, most of us are using 802.11ax, which you probably just know as Wi-Fi 6. And this latest version is all about pumping out higher speeds, being more efficient, and most importantly, handling the dozens and dozens of connected gadgets we all have now.
All right, so we've got the signal and we've got the rules. But what's the actual piece of hardware that's sending and receiving all this information?
Well, that job belongs to the access point, or AP. The best way to think of it is as a bridge. It connects the invisible world of radio waves to the very physical world of Ethernet cables. It's constantly converting data into radio signals and then back again. And the magic of how it does this? It's all in the antenna. The most common type you'll find is the omnidirectional antenna. And the light bulb analogy is perfect. It's designed to give you 360-degree coverage, spreading that Wi-Fi signal everywhere. It's what you want for covering a big open space, like your house or an office. But what if you need to beam that signal a long way and only in one direction? Well, for that, you'd use a directional antenna. It's like a spotlight, focusing all its power into a narrow beam. This is great for things like connecting 2 buildings on a college campus.
And then there's the really clever stuff, MIMO. It stands for multiple input, multiple output, and it's the tech that lets modern routers use a bunch of antennas to send and receive way more data at the exact same time. Honestly, it's a huge reason our Wi-Fi speeds have gotten so much faster lately.
Okay, so we've got our building blocks down, the waves, the rules, and the hardware. But how do we actually put all this together to cover a massive area, like an entire office building or a university?
Well, this is where network architecture comes into play. And it really all boils down to one big choice between 2 different philosophies. Do you want every AP to be its own boss? Or do you want one single boss managing all of them?
So let's talk about those autonomous APs, sometimes called fat APs. They're totally simple and self-contained. In fact, your home router is a perfect example. And that's great for 1 or 2 devices, but can you imagine trying to individually configure and update 100 of them? It would be a nightmare. It just doesn't scale.
And that is exactly why large networks use what's called a split MAC architecture. Now, MAC just stands for Media Access Control, which I know sounds complicated. It's really just a fancy way of talking about all the management and control stuff.
So in this setup, you basically take the brains out of the individual APs and put them all into one central device, the wireless LAN controller. The lightweight APs you see on the ceiling, their only job is to handle the radio signals. Meanwhile, the controller manages everything. We're talking security, updates, configuration, the whole shebang, all from one spot. It's what makes managing thousands of APs not just possible, but actually pretty straightforward.
And there's actually a third, kind of hybrid approach that's getting super popular now, a cloud-based architecture. It uses those smart autonomous APs, but it pushes all of the management functions up into the cloud. This gives network admins the power to control their entire network from a web browser, from literally anywhere in the world.
You know, when you think about the billions of new devices coming online, everything from our cars to our coffee makers, the next big wireless blueprint is going to have to be more powerful and smarter than anything we've seen before. And understanding these building blocks, from the frequency of a single wave to the architecture of an entire network, well, that's the first step to imagining what that future will look like. Thanks for joining us on The Explainer.